Very pleased to have our speaker here from UC Irvine. This is, how do you pronounce it, Hamber?
Yes.
Professor Hamber from UC Irvine. He's going to talk to us about gravitation and give us a very broad overview of the state of the field of gravitation, including quantum gravitation, the state of play, some speculation about where things are going in the future with gravitation. So,
Thank you.
Thank you.
It is a pleasure to be here. So my talk will be about gravity at the beginning and quantum extensions of gravity later on. Now, of the four fundamental forces, gravity, of course, is the one that's been studied the longest since the 17th century. And besides being kind of an immediate fact of everyday life, gravity also has effects on all sorts of distance scales and presents nowadays some of the most challenging problems in physics. It has ramification into microscopic aspects of the universe, right? We think of gravity as affecting the structure of space-time at very short distances, right? That is part of the more modern research into gravity. But also it affects things on the larger scales. In fact, it is the only force that affects things on scales which are, of course, the solar system at first, galaxies, quasars, black holes, and of course, as we'll see, the universe as a whole as well is dominated, its evolution is determined by the equations of general relativity, which is extension of Newton's original gravity to a relativistic domain. So let me just start out by reminding you of the fact that in nature we have four fundamental forces, right? The strong force, which is entirely limited to the size of a nucleus, right? Most of the time. I mean, there are exceptions, namely neutron stars, but it acts on very short distances. The electromagnetic force that most of us are familiar, its action only extends usually to a few centimeters. After that, generally you have screening, you have neutral objects, and long-range forces from the gravitation, from the electromagnetic force usually don't survive. We have the weak force, which again happens at very short distances and is responsible for radioactive decay. And so when you look at larger distances, all you have left over is the gravitational force, which of course is very weak, right? So in order to quantify how weak it is, I hope you can read what's on the screen. It's a little bit on the small side, but you can try to, for example, calculate the force due to gravity that is exerted on two particles, like two protons, and you find that it is many orders of magnitude, right? It's about 10 to the minus 40 orders of magnitude smaller than the electromagnetic force. It is extremely weak, and of course that is one of the mysteries, right? Why is it that it starts out so weak compared to the other forces, right? It is universal, it couples to everything, right? If gravity doesn't couple to something, then that something does not exist, because gravity couples to anything that contains matter or energy, right? So it is universal, it couples with the same force to everything, with the same strength, and another important aspect is that it is long range. It acts over enormous distances, right? And it cannot be screened. It would be desirable, interesting, fascinating if you could screen gravity, right? But we don't think that within the framework of the present gravitational theory, such screening can exist. That screening, of course, is something that happens all the time in electromagnetism, right? And so that is the reason why gravity acts on very long distance scales compared to the other forces. Now, gravity in the modern point of view, in Einstein's point of view, affects the geometry of space-time. In other words, when you have a mass distribution in curved space and then the motion of various objects that move into that gravitational field is determined by the curvature of space-time. Kind of died, so we have a little technical problem. And
we have another clicker.
You have another clicker? Yeah, well,
It works.
it works for a little bit, right? We don't know for how long. So yeah, it's a good thing to have a backup. Now, of course, most of you are aware that this year, 2016, we are celebrating 100 years of general relativity. Einstein wrote down his fundamental equations in their final form eventually in November 1915, in November of 1915, and eventually was able to present the whole theory in a complete way soon after that, at the beginning of 1916. So here's the original paper in German, which is actually quite, I shouldn't say quite easy, but it is certainly quite readable. Right? It is written in the usual style of Einstein, where he tries to explain everything in a simple and straightforward way, and just introducing the essential amount of mathematics that is necessary to understand the basic points without assuming that the reader is actually, at that time, might be familiar with differential geometry. So it's a wonderful reading. Of course, nowadays, because of the internet, we can get access easily to all these original papers, which is kind of wonderful. So the original formulation of gravity was, of course, the one that was presented by Newton in the 17th century. And Newton's point of view is that bodies are attractive to each other because of a gravitational force, right? Within his theory, the gravitational force is instantaneous, and so there is some message exchange between the two bodies, and as a result of that, they interact. And of course, that information is encoded in Newton's equation, or Poisson's equation, which describes the gravitational field, which is a single field, a single scalar, that encodes all the information from the gravitational field. Einstein's general theory of relativity, of course, is quite different and much more complicated in its formulation, because first of all, it is based on a space-time point of view. In Einstein's view, the motion of a body is affected by the fact that space-time is curved. So the body follows the curvature in space-time, not just in space, but in space-time. So there's a curvature of both dimensions, right, which comes in. And so that point of view is quite new. And of course, the equations not only are significantly more complicated than Newton's equations because they're nonlinear, but they also involve many more fields. Instead of having one gravitational field, you have 10 of them. Right? So there's all these components of the metric that you have to sort out to determine this complicated motion in a curved geometry. And the point that he made is that in a curved geometry, a particle will always follow a path that has the shortest distance in space-time, which is referred to as a geodesic. Right? So the equations, of course, have become famous, so you can find them all over the world. In particular, if you go to a locomotive graveyard in South America, you will find these equations inscripted on a rusty locomotive in their correct form with the correct sign, so with the factors of C in the right place, right?
Is there a story behind that?
There probably is, but I don't know what it is. So you can look it up. I'm sure with the internet you can find something more about it. And so the equations state the fact that the curvature of space-time, which is encoded in this case, the Ricci scalar, is determined by the distribution of mass and energy, which is this T, right? And the coefficient that appears here is Newton's constant. So if you look at phenomena around us, right, on Earth, or even within the solar system, you find that the effects of this space-time curvature are tiny. Right? Whenever you have a curved surface, you expect the angle, some of the angles within a triangle to add up to 180 degrees, and that kind of total angle is very close to what you expect in Euclidean geometry. Nevertheless, if you look at structures which are affected by much stronger gravitational fields, whether it's a neutron star, a pulsar, a quasar, or in fact the universe as a whole, you find that the deviations from Euclidean geometry start to become significant, right? And that is, of course, what has become one of the topics of great interest in the late 20th century, early 21st century, is understanding these effects due to strong gravity. Now, some of you might know that your GPS system, in fact, will not work unless you take into account some basic general relativistic corrections. That is, in general relativity, you have the slowing down of clocks in a gravitational field. So if you have a strong enough gravitational field, the clocks will run slower. Now, on Earth, of course, we have a gradient for the gravitational field. So as you go up into the atmosphere, as you go towards this constellation of satellites that determine your GPS system, the gravitational field gets weaker, and you have clocks that run a little bit faster because of that. And that has to be taken into account when you set up a GPS system. Because if your GPS system does not take into account the relativistic slowing down of clocks, your GPS will be off by 300 meters in a month, right? So this building is going to be somewhere across this parking lot, or maybe further than that, right? So these relativistic corrections are quite important. And now, if you go to investigate what kind of situations you need in order to get very significant deviations from classical gravity, then what you need to achieve is something for which the combination of Newton's constant times the mass of the object divided by the size of the object is of order 1. That's where you get strong gravity effects. So that means the mass has to be rather large and the size has to be small. Right? So that means that you encounter a strong gravity regime if you look at things like neutron stars, which are very compact, or black holes, which are even more compact, or in fact gravitational wave and the universe as a whole. It turns out that the universe as a whole is in fact in a strong gravity regime because it does satisfy this approximate equality. We do know, of course, what G is, right? G is Newton's constant determined by the appropriate study of an apple falling from a tree, right? You can determine what G is from that, right? And the mass of the universe is roughly known. Within a few orders of magnitude, we know that the universe contains about 10 to the 80 protons. We also know that that's not the whole story, but roughly 10 to the 80 proton is a reasonably close approximation to the total mass of the visible universe. And we also know what its size is. It's about 10 to the 28 centimeters, if you wish, or its time extent is the age of the universe, about 13.8 billion years. So there is a notion of what is the size and what is the mass of the universe. If you take that combination, we have a regime of strong gravity. Now, gravity also affects things one believes, or some believe, or most believe. It depends a little bit on who you talk to. Some people believe it more strongly than others. But gravity also affects the very short distance frontier because there is in gravity a length scale which is referred to as the Planck length, which is what you can get by taking just the square root of Newton's constant in an appropriate system of units. And that's 10 to the minus 33 centimeters. And that is believed to be a scale at which quantum fluctuations in gravity start to become very important, right? And this is about 15 orders of magnitude above the highest energy or the shortest distance scale that we can study today, because at the LHC, the present energies that can be achieved are of the order of a few TeV, right? So 15 orders of magnitude beyond that, you start to worry about what happens with energetic collisions like they would occur in gravity at short distances. So perhaps at that scale, there is a way to connect gravity to the other forces in nature. That is, of course, a topic of great contemporary interest to understand how gravity fits with the other forces. There's 4 of them. Presumably they are related. People have argued convincingly that the strong electromagnetic and weak force are closely related by what is called the Standard Model, right? But gravity doesn't seem to fit with that at all, right? So some people argue that string theory can provide a unification, but that's very speculative. So one of the first predictions that Einstein made back in 1916, which was somewhat unexpected at that time, in fact he had already a previous calculation in 1913, which turned out to be a little bit off, was the prediction that light would be bent by stars, in particular by the sun. And so that is one of the great successes of general relativity, that such an effect, in fact, can be observed. It was observed right around 1916. Well, of course, World War was going on, World War I, so there was no way of measuring at that time because you needed a solar eclipse. And you needed to travel where there was a solar eclipse, and the first one that was accessible was in southern hemisphere. And so Eddington sent some of his students and postdoc down to Brazil to finally, when an eclipse happened, to do an accurate measurement of whether the location, the apparent location of these stars would be moved. And indeed, the amount by which the star's location was moved agreed pretty well with what Einstein had predicted, which was almost a direct verification that space-time was curved, right? Because one of his predictions was that the fabric of space-time would be curved around massive objects, and the sun, of course, is such a body, and so you would have light from these stars getting bent around the sun. So that was quite amazing for that time, and provided a lot of interest in the popular media. And of course, nowadays, this testing of the bending of light can be done much more accurately. A recent mission to Jupiter, the Cassini mission, was actually able to see the bending of light over very large distances, but with in the microwave regime, where you can have a better control of the errors and the systematics, and you're not as much affected by the light obscuring the apparent location of the body. Even more spectacularly, of course, in recent years, we have seen the existence of gravitational lensing. And so the way gravitational lensing works, as you might recall, is that you have a very luminous object like a galaxy, which is way out there, and then there is an intervening body, which sometimes you see, sometimes you don't, which has a lot of mass, and it happens to bend the light around it, so you get multiple images, right? These disks that you see around are actually multiple images of the same galaxy, which is hidden behind somewhere, right? So you see the images. You can actually spectroscopically determine that all those images are exactly from the same galaxy, and it's not multiple galaxies appearing there. So one of the cornerstone principles, if not the cornerstone principle number one in general relativity, is the principle of equivalence, which was already stated by Galileo in the 17th century. And that principle states that all bodies will fall down with the same acceleration, that the gravitational attraction is universal. It doesn't care whether the body is made out of wood or plastic or stone or metal. The gravitational force is universal, and its universality is encoded in Newton's constant. And that is one of the aspects that actually leads to a formulation of general relativity, which is unique, right? So Einstein's theory incorporates this principle of equivalence, and it's the only theory that has that principle of equivalence built in. It's the only theory that has a geometric character by which all bodies are attracted in the same way, universal way. That is one of the fundamental principles of physics, and so it's important to test it. Galileo was dropping his stuff from the Tower of Pisa, and that was not particularly accurate. Of course, it's affected by the friction of air and so forth. But nowadays, it can be tested, for example, by lunar ranging. You can study how the distance from us to the moon changes to great precision using a laser, because one of the Apollo missions put a mirror on the moon, so you can send a laser beam and have it sent back. So you can monitor that distance very accurately. And nowadays, the equivalence principle is one of the best tested principles in physics. It's accurate to 1 part in 10 to the 12, which is pretty remarkable. So all bodies experience the same gravitational attraction to 1 part in 10 to the 12, right? That's what it comes down to. Now, another important prediction of the general theory of relativity, which came out almost immediately after Einstein wrote down his equations, is that you have gravitational waves. This is very similar to Maxwell's theory, right? In Maxwell's theory, once you write down the equations of electromagnetism, it's not a difficult exercise to see that you can get a wave equation out of it, right? In Einstein's theory, the same thing applies. If you look at least the case where the field is weak, you can see immediately that you have waves. Einstein, of course, was asked at that time whether, waves would be discovered very soon in his theory, and he said, no, I don't think so. It's going to take a long time, probably centuries. So he was not too optimistic. He thought that was just a curious and cute consequence of his equations, but never thought that actually one would be able to devise an apparatus that would be able to measure these ripples in the geometry of space-time. And it actually didn't take too long, because already in the 70s, right, people were able to establish the existence of gravitational waves indirectly. So what Halse and Taylor did, they studied binary pulsars, and they saw that the period was getting slower, right? The precession period was getting shorter and shorter. And they calculated that in these binary pulsars, what you would expect is the emission of gravitational waves. And that emission of gravitational waves would be determined and regulated entirely by Einstein's theory. All the ingredients would be there. It's just a matter of calculating it. And this is the result. So the dots are the observation, and the curve is not a fit. The curve is the prediction of general relativity. There is nothing to fit, and it agrees perfectly. Of course, at that time, grad students looked a little bit different than they look today. So this was Halsey, who was a student of Taylor. And so times have changed. This is 1972 in Princeton. And so now what has happened over the last year is that, in fact, it has been possible to detect these gravitational waves directly by building a detector, LIGO, right, which is based in Livingston, Louisiana, and at Hanford. There's two of them in the US. They're separated by something like 3,000 kilometers from each other, so there's a safe distance apart. And they are located at these two locations, and further detectors are planned around the world as well. And so they're based on a very simple principle. If you have a gravitational wave that comes in, then it distorts space-time. And if it distorts space-time, it means that the distances are affected. So if you have two bodies, right, of mass m1 and m2, or even the same mass, as the gravitational wave comes in, they get together and they go apart a little bit and they start to oscillate, right? And so that means that you can build an interferometer, which is a setup like this, which is in principle actually not too difficult, right, to conceive, where you have a beam of light, because that's what Michelson and Morley used to measure the speed of light at the beginning of the 20th century. So you send a beam of light and you reflect it in one mirror here and another mirror there as it goes through a beam splitter. And so you measure relative distances in two orthogonal directions. And that allows you to detect gravitational waves. So what LIGO detected is fascinating, because what they detected is the coalescence of two black holes, which are about 1.3 billion light years away from us. So this event happened 1.3 billion years ago. So they're very far apart, and it happened a long time ago. And so remember, this is a significant fraction of the total age of the universe when this event happened. And so what LIGO detected was the coalescence of two black holes. And as this happens, there is an enormous, for this particular event, which was detected in September of last year, there is a very significant amount of gravitational radiation that comes out, which is what this indicates here. So you have the two black holes, and then you have the stuff coming out. And this particular picture, of course, is not a picture of the black holes coalescing, but of a numerical simulation of that event, which was done at the Max Planck Institute in Berlin, has been done at other places as well. And so some of you, I think, are in computational physics or computational science in general, computing and so forth. What is so exciting about this is that the whole LIGO experiment would not really have worked out very well unless the tools have been available to actually simulate this from first principles and state exactly what is expected for a phenomenon of this type, which is non-trivial because gravity is a strongly nonlinear theory. Right? So the computers were actually able to predict the waveform of this thing coming out, what specific frequency distribution would come out of the coalescence of these black holes, and that could be compared directly to the signal. And so here is the Physical Review letters that appeared at the beginning of this year, and can't read much of it, but the coalescence, they were able to establish that what came together were two black holes, one of which had a mass of 26 solar masses, 29 solar masses, and the other one 36. So these are pretty heavy objects, right? And they coalesced together to form a single black hole, and out of it came 3 solar masses in gravitational radiation. That is, 3 solar masses were entirely converted in radiation and came out as a big blast, right? And we record that blast 13.6 billion years later, right? And so this is the actual signal that is recorded at one location and at the other location. So one is in Livingston, Louisiana, and the other one is in Hanford, Washington. So they were listening there, both of them, right? And all of a sudden, this signal comes in, and within a few microseconds, you get another signal at the other detector, right? The particular event happened to be in the southern hemisphere. So the signal was first recorded in Livingston, Louisiana, and then a few fractions of a second later was recorded in Hanford, Washington. And in fact, you can overlap those two signals with each other. They fit very well because, of course, the source is the same. They're just being detected at slightly different times, right? So this is a picture from the LIGO collaboration, which shows a rough location, right? They don't have 3 detectors, but only 2, which means they can't triangulate precisely where the source was, right, as far as direction is concerned. But they can put some sort of region to it. And so that is the region for the original event. In fact, in December, they had a second event, right? Remember that this LIGO detector, they've been working on it for something like 20 years. And many people didn't think that it would ever work because they're able to detect deviations in distances which are a fraction of the size of the nucleus. They are able to detect changes in distances between the 2 arms of the spectrometer, which are of the order of 10 to the minus 20 or 10 to the minus 21, 10 to the minus 21 fractional distances, right, which is extremely small. So when you're able to measure deviations in distances which are the fraction of the size of a nucleus, that means that the technology is really refined. This is all done with lasers, and of course lasers tend to be noisy, so LIGO uses some of the quietest lasers that have ever been built. They were actually built in Germany. So they have very low noise because otherwise you will not see these extremely small deviations. And so they have 2 events, and there seems to be a third one too. Now, of course, another prediction of general relativity, which again at that time Einstein was somewhat skeptic about something like that ever being seen, is the prediction of black holes. That is, that you would have objects which are very compact and for which you have a horizon, which means that if you emit light, the light gets reattracted into the black hole, and the object appears to be black because no light can really escape out of it. That prediction was done, in fact, in 1916 as well by Mr. Schwarzschild, right? Schwarzschild was at that time a professor in Berlin and was talking regularly to Einstein. And well, he was sent to the Russian front. Of course, when you get sent to the Russian front in the winter, there's nothing to do. So you don't shoot, everything is frozen, so you go down underground and you either play chess or you look for solutions of the Einstein equations, right? You have a lot of time in your hands. And so this is what Schwarzschild did. He found this black hole solution. And so that's been around a long time. And nowadays, of course, we know that this is not just some mathematical construct, but that black holes exist. And there is one actually pretty nearby, because our own galaxy has a black hole at the center whose mass is about 10 to the 6 solar masses. And it's very hard to see because there is a lot of dust in our galaxy, so we don't have a good way of seeing in that region. But nevertheless, what people have done, including a group at UCLA under Andrea Ghez, they've monitored the movement of stars in a certain region over many years. And from the movement of the stars in that region, they can precisely pinpoint where the black hole is and what its mass is, right? So in fact, nowadays, of course, it is believed that just about any galaxy has a black hole at the center, right? Not hard to see, but you can estimate its effect indirectly. So the last scenario where gravity has an important influence is in cosmology on the very largest scales, where, of course, the evolution of the universe since the Big Bang is determined by gravitational forces, right? The universe stays together because everything attracts everything else in some way, right? That is at least what you would believe in a first approximation. And so the expansion of the universe is dominated by these gravitational forces between galaxies and clusters of galaxies and so forth. And Einstein's theory gives a precise form to the equations that are supposed to be obeyed by universe, at least in a first approximation where you assume that it's homogeneous and isotropic, which means it looks pretty much the same way in every direction and doesn't have too many fluctuations in mass density and so forth. And I think you probably have a hard time reading that equation. But within the Einstein theory, you can clearly recognize that there are 4 different contributions which act differently and which affect the expansion of the universe in different ways. The first component is radiation, that is massless particles. Most of it is photons. Those are important in the early stages of the universe, which is over on that side. So photons make the universe, or any massless particle makes the universe expand in a certain way. Most of the effect of the photons are gone by now, and the expansion of the universe is determined more by matter density. Everything that is made out of ordinary matter, or maybe some unusual matter which is similar to ordinary matter but is nevertheless non-baryonic. But what Einstein also found is that there is a term that you can add to his equations which is referred to as the cosmological constant term, and that is in fact the term that is here at the very end, and that is what determines the expansion rate of the universe at very late times. And we have recently found in 1999 that there is this cosmological constant term as well, and that the universe is actually accelerating in its expansion because of that. And that was a big surprise too. So again, one more surprise that comes out of gravity from the last 10 or 20 years, right? And it's not just gravitational waves, but black holes and the cosmological constant contribution. And so the issues that now interest people that work in the general field of gravity is ultimately, for example, what is the geometry of the universe? Is there just a single universe? There might be multiple ones. We could be part of some sort of multiverse, which would be consistent with Einstein's equation to some extent, because you would have horizons and you would not be able to detect some other universes because they're outside your light cone, right? And when it comes to understanding what the source of this curvature of space-time is, there's actually more than one candidate by now, because we're all used to ordinary matter, which is what the sun is composed of, right? Protons, helium nuclei, and so forth. But people do know by now also that there is a lot of dark matter. And this dark matter is not visible, but it's there because it affects certain properties of galaxies. So there has to be a lot of other stuff that is not luminous, that we don't see, but we know indirectly it's there. So dark matter is a big mystery, and the cosmological constant is referred to usually as dark energy, and that is there as well, and one doesn't understand where that is coming from either, except it looks like it fits nicely into Einstein's equation. So the state of the art nowadays, as far as cosmological, astronomical observation, is that the stuff that we're familiar with, the material that we are made of and this building is made of, only accounts for 5% of the total energy content of the universe, which is a fairly small fraction. Namely, about 70% of the energy content of the universe is in the form of dark energy or cosmological constant, which is some sort of vacuum energy, right? And 25% of it is dark matter, whose origin one doesn't know. It's not clear what dark matter really is. It depends on who you talk to, right? Astronomers will tend to say, well, in the old days, they used to say, well, they're brown stars. They're stars that just float around. They're not very luminous, but so we call them brown stars. That's ruled out because objects like that are too heavy. And so some astronomers will say, well, it's Jupiter-like objects. So they're a little bit smaller than a brown dwarf, and they emit hardly any light. And so that's what some astronomers believe. Particle physicists think that instead it's some sort of exotic particles, like neutrinos or brothers and sisters of the neutrino, so-called sterile neutrinos, or maybe supersymmetric particles, or maybe black holes. Right? I've talked to people that said, well, maybe they're just solar-sized black holes, and they sit there and you can't see them because they're black, but nevertheless they contribute to the mass of the galaxy. So this is a very interesting problem, trying to determine what dark matter is made of. It's almost more an experimental or observational problem than it is a theoretical one, because the theorists really can't say much about it. I mean, We can talk about the rules of quantum mechanics and the rules of building atoms and molecules, but we can't say a whole lot about a new type of matter that is non-luminous. Right, so this was the classical theory, right? Now, we do know that the universe is governed by the laws of quantum mechanics, right? Everything in the universe is affected by quantum mechanics. Quantum mechanics, the Schrödinger equation, the Dirac equation, whichever equation is your favorite to describe matter, right? That is all based on fundamental principles of quantum mechanics, except possibly gravity, right? But it seems unlikely that gravity has a special status, that it is not described by quantum mechanics. So one of the, I think, most interesting aspects of modern research, according to some, is try to understand how to combine quantum mechanics with gravitation and see what comes out of it, because the results could be rather interesting and unexpected. And well, to this day, there are people that think that maybe this is not possible. I don't belong to that class, but I've encountered people that actually will say that perhaps the two are incompatible. And I don't believe that is the case. I think that we do know that quantum mechanics works extremely well, right? There are ways of testing quantum mechanics which ultimately come down to a number, which is that quantum mechanics is good to 1 part in 10 to the 11 or 10 to the 12. That is the so-called gyromagnetic anomaly of the electron, where the agreement between theory and experiment is 1 part in 10 to the 12. So quantum mechanics works extremely well, even in a relativistic context, for electromagnetism, for the strong interactions, for the weak interactions as well, but the best test, of course, is electromagnetism. So one should really think seriously about what happens when you combine quantum mechanics with general relativity. And so just to give, an overview of what you think naively should happen, right? You have on the one hand the characteristic features of general relativity, which is this curved space-time, right? And on the other hand, you have the characteristic features of quantum mechanics, which is the existence of fluctuations which are proportional to h bar, right? So quantum mechanics has a new constant that determines the size of these quantum fluctuations. And so what you try to do is combine the two together. If you combine the two together in a naive picture, what you would expect is fluctuations in space-time, right? Why should it be any different? And so you expect that space-time all of a sudden acquires some sort of foam structure, right? And this is what Wheeler referred to as space-time foam. Here's a picture of John Wheeler. I think some of you might have encountered him at one point or another. Remember that Richard Feynman was a student of Wheeler. And Wheeler is the one that suggested to Dick Feynman to look into path integral. He says, well, there is this formulation which I think we should develop based on path integral amplitudes. And so he was very influential in a number of ways. And here, in fact, you see the classical trajectory versus the quantum mechanical one determined by a path integral. So Wheeler already in the 60s was thinking about how you would combine the two theories together, never had any doubts that it could be done. And so one of the first things that you would be led to is to make some sort of comparison between gravity and electromagnetism. And well, there are similarities and there are differences. There are, first of all, very substantial similarities, because if you look at electromagnetism, you have two sources, and the field between the two is determined by the standard solution for a point source. If you have a single point source, the potential is just 1 over r. The strength is given by the electric charge squared, right? And in gravity, of course, you have a similar situation, at least in Newtonian gravity, but of course also in Einstein gravity in the weak field limit when you look at static solutions. You have 2 point masses and they generate a field, and for a single mass you have a 1 over r potential. So the mathematics of it at first looks very similar. Nevertheless, Einstein understood that there are a lot more fields in gravity than there are in electromagnetism. In electromagnetism, you have a 4-vector. You have, in other words, the scalar potential and the vector potential. And in general relativity, you have to have a 4x4 matrix, right? If you have a vector field, you can show that you have the notion of opposite charges. So if you have a 4-vector, you can have plus and minus charges. But you can never have that if you have a a 4x4 matrix. So with a 4x4 matrix field, the interaction will always be attractive. Now, if you look at the quantum mechanics of this process, then you realize that what you're going to have, it is natural to have fluctuations in the field, which means that all of a sudden, in a quantum mechanical view of the universe, instead of having field lines, which are nice and smooth, if you look at them very closely, you will see fluctuations. So a general feature of a quantized gravitational field is that you will have something that looks like the Heisenberg uncertainty relations, right? And so in electromagnetism, they take on the form of delta E times delta B. Fluctuations in the E and B fields have to be greater than h bar. And in gravity, you will have something analogous. Also, of course, you have particles, right? In electromagnetic field, you have photons. And in the gravitational field, you will have something similar. Now, the effect of these quantum fluctuations are visible in electromagnetism in a number of different ways, including a so-called lamp shift, because the quantized gravitational field actually affects the spectral lines in the hydrogen atom. And so that has been known for a long time, has been accurately measured. And it also leads to a modification of the 1/r force, because in electromagnetism, what you do have is that, well, normally, if you think of empty space is empty and there's nothing in it. But in quantum mechanics, you have fluctuations, which means emptiness does not exist. There is always something that fluctuates even in the vacuum. And so what you have in electromagnetism already is that in totally empty space, there is a finite probability of creating a pair, an electron-positron pair, and that pair will act like a dipole. Will last a short time, but nevertheless, it will make the vacuum a dielectric substance. And this is what is indicated here, and as a result of that, the quantum mechanical vacuum gives rise to screening in electromagnetism, which is measurable. It's something you can measure even in an atom. It's so-called Uhling correction. So there are all these wonderful quantum mechanical effects that arise because of fluctuations, and they're quite well known and understood in the context of the electromagnetic field. So one of the important consequences as a result of that is that whenever you have a point source at the origin, it is surrounded by this soup of virtual particles, of elementary dipoles, which means that you have a screening which depends on the distance at which you are from the source. So if you get closer to the source will be weaker because you don't have the screening effect. So in other words, there is no notion anymore of coupling constants that are constants. Coupling constants actually change over distances because of this quantum mechanical effect, right? So that is something that has been measured at the CERN accelerator. You can actually see the effects of the screening due to the vacuum. Now, there is another theory, before you plunge into gravity, there is another theory that has generated a lot of very significant headaches for people working in particle physics and in fundamental interaction, and that is the strong interactions, because the strong interaction, which describes the binding of quarks by gluons, right? These quarks, you can never see them because they're completely trapped inside nuclear matter. Those interactions have a coupling strength which is of order 1, which means that it's not weak, so it's very hard to treat analytically, right? And so these quarks are bound together by some sort of flux tube field, which is what I indicated here. And that means that the strong interaction is in fact one of those theories where analytical methods have become less and less useful because of the strength of this self-coupling of these gluon fields. And what has happened over the last 20 or 30 years is that people in the field of particle physics working on quarks and gluons and so forth have taken advantage of Moore's law. What is Moore's law? Moore's law is that computer power doubles every 18 months, right? And that there have been very dramatic developments in the power of large-scale computing over the last 30 or 40 years, which means the problems that were originally not amenable to any sort of numerical treatment because the numerical answers would be not particularly credible and based on simplistic assumptions and so forth. Those numerical methods nowadays have become very powerful and influential and very accurate, just like we saw before in the case of the coalescing black hole studied by numerical relativity. And so here is the case of one of these machines that is used to study the strong interactions. At Fermilab, there is a whole cluster building. It's called the Feynman Computing Center. And so I don't think you can see the picture, but there's racks and racks and racks of PCs that are strung together through some high-performance switch to study the strong interactions. So now if you translate this intuition and understanding to gravity, then what you expect is something similar. That is that in a quantum mechanical treatment, you will have fluctuations of the gravitational field. So if you look at the field closely, you will see these macroscopic fluctuations, and they should have observable effects. They should have observable effects as in electromagnetism, as in the case of a strong force. And well, the problem is that they're not easy to calculate. And the reason why they're not easy to calculate is, in my opinion, ultimately because this is a nonlinear theory, right? Now, nonlinear field theories are very tough. QCD was the first example. The strong interaction was a first example. I think gravity is secondly a second example. I think some of you are mathematicians. You do know that the number of ordinary differential equations, nonlinear ordinary differential equations that you can solve analytically, you can count them on the fingers of your right hand, right? There's very few nonlinear equations that you can find an exact solution, right? And so in that case, I think, when people started to use computers, they discovered all sorts of wonderful behavior, right? Limit cycles, Poincare trajectories, and so forth, Lyapunov exponents, and all sorts of interesting features that you can't see by just looking at simple examples. And of course, fluid flow, right? The flow of water in your bathtub is another example where you have complicated solution to the Navier-Stokes equation. So gravity very much is probably belonging to that class. It's a highly nonlinear theory. Why is gravity highly nonlinear? Well, because gravity couples to energy and momentum, and the field itself carries energy and momentum. So the field couples to itself. The gravitational field has energy and momentum, and therefore it gravitates, right? That is not true of electromagnetism. A photon will go through this room from one end to another without being affected by anything. Two photons can just go past each other and have no interaction whatsoever. The interaction, you can only see it when you look at the so-called box diagram of QED, which is extremely weak. So two photons will go right past each other like this and feel no effect. Gravitation, gravitational fields, graviton don't do that, because they both carry energy and momentum, and therefore they will gravitate. So this nonlinearity is crucial and is one of the major stumbling blocks in actually trying to understand what is going on in this theory. Nevertheless, we are aided by the fact that we know exactly what the equations look like, because we don't want to modify the theory. We want to just take over Einstein's theory, right? So the theory you start out with is the theory as written down by Einstein. And in fact, it was Richard Feynman who proved in the early 60s that the Einstein theory is unique. There's no 2 or 3 different Einstein theory. If you take a particle, according to quantum mechanics, that has 0 mass and spin 2, you get Einstein's theory. It's the unique theory that describes that. So gravity, we know what the action, we know what the equations are. There is no need to hunt around for a modified theory of gravity because it doesn't exist. It's unique, right? So now the technology, I have another 5 minutes, so I'll show just a few pictures, and then I plan on finishing on time, right? So the basis, of course, of this approach is the Feynman path integral approach, which is a modern way of doing quantum mechanics. And it turns out it's eminently suited to be put on a computer, right? But first, let me point out what people have done and which doesn't work. Right? So what people have done is they've used perturbation theory to study this quantum theory of gravity. So you start out with a graviton, and then that graviton can split in 2, and it can split in 4, and so forth. And so you can use then perturbation theory to see what happens when this graviton propagates and interacts and so forth. And the formulas to study this splitting and interaction is basically quantum mechanical first and second order perturbation theory, right? So if you remember what that is, physicists certainly remember that, you have energy denominators, you have matrix elements, and then you sum over intermediate states. And here it's a little bit more complicated because you do it in 4 dimensions. And the end result of that is that you get infinity. So as soon as you have these gravitons interacting with each other, you get infinities. And if you look at simple diagrams, you get one sort of infinity. If you look at more complicated diagrams, the infinities pile up. It gets even more divergent, right? And so perturbation theory, the methods that you use for QED don't work for gravity because you get infinity plus infinity plus infinity at every order. And of course, the conclusion, and I'm talking here about the fact that you also should include a cosmological constant, and we don't have time to go into that, but that's an important fact of this. The conclusion is that perturbation theory in this Newton's constant, when you do the quantum theory, doesn't work at all. And many people at that point have taken the attitude that this is a reflection of some fundamental incompatibility between quantum mechanics and gravitation, and that you should just give up and do something different. And so that something different is called supersymmetry, n equal 8 supergravity, or even string theory, right? So you abandon the beauty and the simplicity of Einstein's theory, and you decide that you're going to add more particles and reduce these elementary particles, make them into strings, and that is what is being done by a number of people who are very active in this field, who claim that the string theory is the ultimate answer to all the diseases of gravity as well as other diseases of particle physics. Nevertheless, anybody that has looked at many-body physics for a few years will realize that there are a lot of very interesting problems where perturbation theory fails completely, and I'm sure also some mathematicians are quite aware of that. And if you're an engineer and you're dealing with fluid flow, you know that you never get turbulent flow out of laminar flow or out of simple solutions of the Navier-Stokes equation. So the failure of perturbation theory actually doesn't mean that the theory doesn't exist. It just means, probably in my opinion, that the mathematical methods you're using are just inadequate. That you're relying on the expansion, assuming analyticity in G, on an expansion that presumably does not exist. And that is the case for a lot of interesting situations in physics where perturbation theory is useless, and nevertheless, the ground state that emerges after you do a more sophisticated calculation is very interesting. Superfluids, superconductors, phase transitions, turbulence, these are all screening in a Coulomb gas, and many others. These are all phenomena where perturbation theory doesn't work, and nevertheless, there is some very interesting physics come out of it, and you just have to be a lot more sophisticated. So this can be applied to gravity, but it means that you have to find other ways that are not perturbative, which means you have to put it on a lattice. And well, how you discretize space-time is something that was described by Descartes in the 17th century, and more lately by mathematicians that work in the field of piecewise linear manifolds, and in the case of general relativity by Regge and Wheeler back in the 60s. And the idea is that you just triangulate this manifold, right? So you just build up things out of four-dimensional analog of triangles, which are called simplices, and you construct your space-time geometry based on that. And so then you have some sort of a lattice, and this lattice can be put on a machine, right? And that was something that you couldn't do 30 years ago, but nowadays it starts to become a lot more feasible because machines are becoming so exceedingly powerful. And well, up here I actually have a picture of John von Neumann sitting in front of the ECL project in Princeton, right? John von Neumann, remember, designed the first digital computers based on vacuum tubes. I gave a very similar talk in Berlin, and half of the audience got up and said, what about SUSE? Because, of course, there was a German computer scientist who, during the war, had done something quite similar to what von Neumann had done. But nevertheless, I think we still believe that John von Neumann was very influential in that. And this is, by the way, a non-von machine because it's not sequential. A lot of what is being done here is parallel computing. So you actually use this lattice. You can distribute the lattice on these parallel processors. And so you find that this theory has a very interesting phase diagram, and one of the main aspects that comes out of it is that Newton's constant is no longer constant, but it varies slowly. It increases with distances which are of cosmological size. And so that is something that we look forward to someday being actually discovered in satellite experiments. So the scale for this happening is a scale which is actually larger than galactic clusters. So it will, I think, take a while, but there are certain theoretical predictions that can be refined. And there's a lot of satellite experiments that have looked at gravity on very large scales recently. So the hope is that something like this will be observed at some point. The picture that we have is a so-called vacuum condensate picture of gravity, which is in fact quite similar to what you have in other field theories where there's some sort of vacuum condensation as well. And well, that might resonate with some of you, and it might not. And it's a tricky subject to describe in a short talk. But this vacuum condensation is something that really affects the ground state of the theory quantum mechanically and can never be seen in perturbation theory. You can never see this condensate by doing perturbation theory. And so I think that's where we are. This is the last slide. Right? So the last slide is supposed to show you where Newton started, right? Newton started right here at the bottom. That's a classical F equal ma, right? And then we have the development, well, historically, of course, the first development is adding the finiteness of the speed of light, which goes up. So now you have light cones and you have special relativity, 1905. Now, quantum mechanics adds a new dimension, which is the existence of h bar, which explains the existence of atoms and molecules and so forth. And quantum field theory is actually a combination of the two, so you promote quantum mechanics to a relativistic setup. And so you get the Dirac equation and so forth. Gravity is an orthogonal direction, right, which starts out in 1916. It's in modern formulation. And Einstein's theory is, in fact, a relativistic extension of that. So it's up here. So that's GGR. So if you look at cosmology, cosmology, from what I've tried to convince you, is actually the other vertex of this cube, because it does combine elements of quantum mechanics, elements of relativistic theory, right? The universe as a whole cannot be understood in terms of Newtonian mechanics. You need Einstein's theory to understand it correctly, because remember, Gm over r is of order 1 for the universe as a whole. And the quantum mechanical aspect of that is, I think, essential as well. And so that's the conclusion of my talk. All right, thank you very much.
Questions for our speaker?
You had, so this dependence of G on a distance, is that a counterpart of asymptotic freedom in PCD?
It's the counterpart of that, yes, yes.
Do you see something we can learn from asymptotic freedom to inject into this?
Yes, of course. I mean, we are building this whole edifice of the quantization of gravity on the experience that people have gained in the context of other quantum field theories. And of course, asymptotic freedom and the strong interactions and non-abelian gauge theories is an essential component of that, because things have become more complicated. At that time, people realized that you could have anti-screening or screening both at the same time, depending on the structure of ultraviolet fixed points and so forth. So yes, it's built up on that, but of course, asymptotic freedom was originally discovered in perturbation theory, right? And then later on, people found out that if you just look at perturbation theory, then you should have free quarks. There should be free quarks everywhere, and none of that was seen, so then confinement came in. Here, perturbation theory doesn't seem to work from the very beginning. You don't really get anywhere. So you have to think a little bit harder. And, but nevertheless, I'm a firm believer in the fundamental validity of the underpinnings of the pillars of quantum field theory, which are based on the Feynman path integral approach, on the rules of quantum mechanics, the rules of quantum field theory is encoded in endpoint functions and the Ramization group and fixed points and so forth, right? That all carries over, and the path integral, of course, right?
Mathematically speaking, do you predict that the gravity, this formulation of gravity, would require something analogous to non-abelian description of gluons, or we already have that within Einstein equation? Or are you looking for
We already
additional
have that.
structure? So
You already have
nothing
that.
additional.
No. The whole point here is that you try to understand gravity by itself, right? And without the additional ingredients that some people like to add to it, right? With the recognition that this is a highly nonlinear theory because gravity gravitates, and that perturbation theory is unlikely to be any sort of guidance on what the true ground state of it is. And I think 30 years ago, it would have been impossible to get anywhere doing this. But I think with the advanced in digital computers, we get a better handle on nonlinear field theories, nonlinear aspects in general.
If I understood correctly, your discretization of space-time is
Yes.
something you just input. It's not
Yes.
dynamically emergent. It's given.
No, it's dynamical. It's dynamical from the beginning.
It's dynamical, but is it emergent or not?
It's put in by hand.
It's put in by hand.
Yes,
So
but that is Feynman's point of view. I mean, remember,
I know. So
Feynman points out that to define a path integral, you need a lattice, because the Feynman paths are Wiener paths, and they're non-differentiable, right? So the derivative does not exist at any one point. So in Feynman and Hibb's book, they go at great lengths to describe how you define a path integral through this discretization, where in fact the derivative, if you were to write anything like a derivative, the derivative would not exist anywhere because they're Wiener paths, right? So we have that same pragmatic point of view. So now instead of taking a non-relativistic particle moving through space, we take gravity, and we said, well, in order to define the path integral, you need to laticize it, right? And so we laticize the same way that people laticize computer games, right? When you have a first action game, right? Everything is triangulated around you, right? So this is a triangulation of four-dimensional space-time, nevertheless, right? So you're not dealing with triangles, but you're dealing with simplices. And that is a way of regulating, of defining the path integral. What the ultimate structure of space-time might be at distances of 10 to the minus 33 centimeters, I don't know. I'm a pragmatist, right? So I like to introduce the path integral to make this quantum field theory well defined as a calculational tool, right?
the reason why I ask is because this is a standard criticism of this so-called naive discretization of space-time. People nowadays saying the discretization should be emergent from the dynamics itself. It should not be put in artificial, because it's kind of, space and time talk to each other.
Good luck. I wish them good luck.
Okay, so
Yes.
you are not. Okay.
I wish them good luck. As I said, my point of view is pragmatic. That is, you read Feynman's book, you need a discretization. I look around, what is a discretization for gravity that might work in this case? Well, it was written down by Reggie and Wheeler. If you have MTW, right, the phone book, Meissner, Thorne, Wheeler, Gravitation, the black book is chapter 48. Chapter 48 describes the Regge-Wheeler discretization of gravity. It's the best we have. It's based on triangulation. That is a way of regularizing and defining the path integral. If somebody has some other way of describing the microscopic structure of space-time through some other entities, whether it's posets or loop spaces and so forth, fine. I wish them good luck. If they can get that under control. They end up doing analytic calculations, of course, most of them, which I think are tough. So, yeah.
Other questions?
Yes. Louder.
One question. What do you think about the existence of gravitational solitons? Do they really exist? I mean, I can calculate them, but...
Of course. Well, that is a very interesting subject, and they're called geons, by the way. And Jim Hartle visited us, a year ago, and I invited him to a colloquium, and I asked Jim, you might have heard of Jim Hartle, Hartle-Hawking wave function, and so forth. I said, what about gravitational solitons? Because I talk about them, and I never have a specific reference. And he says, well, I did that when I was a postdoc in Princeton. It was geons. Wheeler suggested that we look at these gravitational instantons and geons. We did a few simple calculations, and we found that they will fall apart. In other words, they will not stay together for too long. And I said, what about later? So that's about the state of the art. So I don't know. I think, this numerical general relativity is very interesting. I expect that there will be soliton solutions. Probably not easy to find analytically, but people will be able to find them numerically. I think it's a very interesting subject. You have a lump of gravitational energy, radiation, gravitational field. Will it stay together? If you have the right conditions, if you have the right initial conditions, perhaps. That is a very interesting project. I think I've been around a lot of numerical relativists, and usually the only thing they've been occupied for the last 5 years or so has been LIGO, right? That was their primary concern. They needed to find out what the waveforms look like when you had two coalescing black holes. And anything else was irrelevant, right? So development of numerical codes to do those kind of things, to take into account singularities from the existence of horizons and so forth, that was. So I haven't heard much about solitons. And, I did hang around some of these characters for quite a while. But,
You take Einstein's equation.
Of course.
You can calculate soliton solutions directly from there. There exist soliton solutions.
Yes. Yes. How long do they live? Do they?
But you said you have to calculate it numerically. But from the Einstein equation, you can also calculate analytically soliton solutions.
That's what Jim Hartle was doing. But he said they were unstable. They're called geons, as far as I know. If you have some references, I'd love to see anything that is related to that. I'm not a classical relativist, really. My field is more particle physics. So I usually, don't dwell into these classical aspects too much. But I think there is an enormous field out there which is investigating, interesting nonlinear properties of the Einstein field equations for geometries that maybe have a lot of symmetry and some which don't have any symmetry, and see whether you can have metastable solutions of some sort. I mean, even if they eventually fall apart, it'd be interesting to see if you can have some which are long-lived. So I know very little about that. I'll be happy, if you can talk or send me a reference or anything.
Good question.
You had a slide last but one. I noticed in a split of a
Yes.
second that there was a predictions word.
Yes.
Do you really have predictions from your letters?
Yes, well, the predictions are that, it becomes more and more difficult to quantify as you go down this list. The first prediction is that the coupling constant will actually change in scale. Newton's constant will not be constant. That is one important prediction. The other predictions are that there's modifications in general to gravity at very long distances, which means that the Einstein field equations are modified by some non-locality due to the running of the coupling constant. And so that affects matter density perturbation, it affects the so-called slip functions. It affects a lot of things that are calculated currently in cosmology. People, when they fit Einstein's theory to satellite data, like the cosmic background radiation and so forth, they use very few parameters. They never assume, for example, that G varies. They always assume that G is constant. They just fiddle with the amount of dark energy versus dark matter, and that's about it. So they don't build that in. So there are other indices, other modifications that have to do with matter correlations and so forth. So there are quantum mechanical effects which are extremely weak. I think you will only see them when you go to large distances, but which I think should be there. What I've been trying to say through the talk, that it is a general feature of quantum mechanics that couplings are not constant. It's a general feature, right? That it happens in all quantum field theories that we know about, and gravity should not be an exception. And trying to quantify that is the challenge. Seeing, exactly how does it vary and whether it's visible today or maybe in the next 10 years. The thing is that these satellite experiments are getting more and more sophisticated. The US and Europe are spending a lot of money in putting up these satellites in orbit, and they're getting exceedingly accurate data, right? So the hope is actually the field of observational cosmology will improve even more so over the next 10 or 20 years. So there's going to be some good data, hopefully.
Last question. Not, let us thank our speaker.
Thank you.